morning, everyone. Is there questions about the homework that's due tonight? Anybody? Of course, tonight is the 3.2 through 3.4, the intersection, union, mutually exclusive, and complement stuff. All right. And then, of course, the additive rule of probability. Well, today we're going to go over a couple different types of conditional probabilities. Get into chapter 3. Now, this isn't something that is explicitly said to be covered in this class, but I think it's a really neat topic. So we'll kind of just touch it in each of the sections. We won't go really in depth. Right. Okay, here we go. So conditional probability. Basically a probability with a condition, all right? So the event probabilities we've been discussing give the relative frequencies of the occurrence for unconditional probabilities because no special conditions are assumed. What we're going to talk about in this section is a conditional probability. It'll be what's the chances of something happening given we know that a certain event does happen. So what are the chances that it rains outside given it's cloudy? That's going to be a lot better probability than just what's the probability that it's going to rain outside. You kind of see what's going on there. So we're putting a condition on it. The given symbol is this little line right here. All right? So the way that that's pronounced is probability of A given B. So let me write that up. Given. The second thing is what's been given. So we know B is happening. What's the probability that A happens if we know B is happening? Right? So it's pronounced is equal to the probability of A given B. That's what it means, right? Probability of A given B. Let me go see. Sorry about that, guys. Okay, so probability of A given B. Let's see. Okay, that one writes a little bit better. All right, and then there's a formula that we're going to assign to it. So this is the English definition, probability of A given B. So what are the chances that A happens if we know B is happening? Right? And there's a nice formula that tells us. So let's look at the die toss experiment. Right? So we know a toss of a fair die is 1/2. So the toss of an even number. So what are the chances we get an even number on a 6-sided die? We've already discussed that the chances are 1/2, right? 3 out of 6. But suppose we're given the information that on a particular throw of the die, the result was a number less than or equal to 3. So what are the chances it's even, given we know it's 3 or less? So how many even numbers are there that's 3 or less? Just 1, right? So our chances are only going to be 1 out of 3, or 1/3. All right, that's kind of how this works. All right, and there's a nice formula that'll help us come up with this value. You know, where we don't have to just abstractly think about it. All right, but that's what given means. That's what conditional probability is. Here is the formula for conditional probability. To find the conditional probability that event A occurs given that B occurs, divide the probability that they both happen divided by the probability that B occurs. So that's the formula. The intersection divided by the probability of the given value. Now, of course, if the probability, thank you very much. Appreciate it. Thank you. We had to scour the education building looking for markers. Of course, the probability that B happens can't be 0. B has to happen. Right? If the probability that B is 0, or if it's not cloudy at all, then it's definitely not going to rain. Right? It can't rain if there's no clouds. So there's the formula. Probability of A given B. Let me rewrite it here. I think that's the same marker. Bless you. Probability of A given B is equal to the intersection of the probabilities divided by the probability of the given event. All right? So there it is. Probability of A given B. Pretty simple formula, really. You know, and then we can go ahead and solve for any of these 3 unknowns as long as we know 2 of them. Okay? And that'll be how it is on your homework. It'll give you 2 of them, and you'll have to solve for the 3rd. Okay? So let's look at an example of it. The examples of one of my favorite games, right? And it feeds in well with this weekend. The U.S. Open starting tomorrow, so we could talk about golf. All right? So, the Hyatt Company is developing stuff for business golfers. People go away on business. A lot of business gets done on the golf course. What they wanted to do was to determine if a person cheats on the golf course, does that mean that they will lie in business? You know, it's kind of a character issue is what they're thinking here. You know, if you'll cheat out there, then you'll cheat doing anything is kind of what they're talking about. Okay? So, the study revealed that 55% of executives admitted that they had cheated at golf. And that could be anything from moving your ball slightly to actually taking less of a score, right? Any type of cheating. Also, 20% of the executives admitted that they had cheated at golf and had lied in business. So that's our intersection, cheating at golf and lying. Given that the executive had cheated at golf, so that's our given, what is the probability that the executive had also lied in business? So let's define A and B. So event A is the executive cheated, so the probability of A is 0.55, right? That's given to us in that previous paragraph. At 55%, so the probability is 0.55. If we let B be the executive had lied in business, which we're not explicitly given the probability that the executive lied in business here. Do you guys see that? All we're given is the probability that they had lied in business and cheated. So they gave us the intersection of the events A and B. It's not even really asking for the probability of B here. All right? That's not what we're asking for. So from the study, we know that 55% of executives had cheated at golf, so P of A equals 0.55. Now executives who both cheat at golf and lie in business, so that's the intersection, right? That's why it has the word and not or. The formula, of course, has the intersection of A and B. So from the study, the intersection is 0.2. We want to know the probability that an executive lied in business given that he or she cheated at golf. So if we know they cheated at golf, what's the probability they lied in business? So all we do here is just simply plug it into the formula, right? So we do 0.2 divided by 0.55. Do that in your calculator. 0.2 divided by 0.55 is 0.36. This is rounded up to 4 because it's 36, 36, 36, so the 3 gets rounded up to a 4. Right? I'm not asking you guys to come up with these percentages, right? This stuff will be given to you in these problems. You'll just have to plug it in the correct place, right? Kind of a plug and chug thing. Right? So really, now that we know 0.364, you know, if I was given this 0.364 as the conditional probability, and then given probability of A, I could solve for the intersection there by multiplying both sides by the denominator, by 0.55. Right? Right, not too crazy here. None of these questions are going to be super difficult. They're all going to be pretty straightforward with this conditional probability. Really, what I want you to remember, now I will give you that formula on the test, you just have to know what goes where. The thing that's given always goes in the denominator. Do we see that? This was B given A, not A given B. If this had said A given B, the numerator would be exactly the same, right? It's still the intersection of the two events. But the denominator would have changed to B instead of A. Right? Probability of B instead of probability of A. It's always whatever the given thing is always what goes in the denominator. Right? So let's look at one more example. That's an interesting one about smokers. It goes a little bit farther than I wanted to go. But it talks about smokers versus getting cancer. What's the probability that you get cancer given you smoke? So I'm not going to go through everything, but I kind of want to look at it. So probabilities of smoking and developing cancer. I mean, everybody in here probably knows somebody that's developed cancer from smoking, whether they're a relative or a friend, right? Right? So smoker, yes. Developed cancer, no. So these numbers are actually pretty small, right? But you notice that if you are a smoker, you have almost double the chance of getting cancer than if you aren't a smoker. You see that? It's still relatively small, but 3% is roughly half of 5%, right? It's a little bit more than half, but pretty close. So basically, smoking doubles your chances of getting cancer. That's what this is saying right here. All right? Now, a lot of things lead into these people, right? Especially hereditary. Genetics is really the biggest factor in whether you develop cancer or not. Right? So of these people that are smokers, look how many of them didn't get cancer. Only 0.2. Especially when we compare it to the non-smokers. 72% or 0.72 of the people that didn't smoke never got cancer. So there's a lot of in between right there. This is definitely empirical support for the fact that smoking causes cancer right there. Everybody see that? Now he goes through and talks about some complements and some conditional probabilities. But what I want to do is just look at the very bottom one, just to kind of stress this point home. Right? So, in a like manner, the conditional probabilities of an adult male non-smoker developing cancer and not developing cancer. So that's what why it's complement, because it's not developing cancer instead of developing cancer. So here are the chances that they get cancer if they don't smoke. Here's the chances that they don't get cancer if they don't smoke. So that's pretty Basically, you only have a 4% chance of getting cancer if you never smoke. You have a 96% chance of not getting cancer if you don't smoke. That's pretty hard evidence right there. Look at these two. Probability of B given A. Probability of getting cancer given you smoke, 20%. 1 out of 5. 1 out of 5 people will guarantee to get cancer if you smoke. Pretty. Now, it doesn't guarantee that you're going to get cancer, all right? This is not getting cancer given you smoke, still 80%. But 20%, I mean, that's a big difference from this number, right? So I just wanted to kind of show you this to show you evidence to not smoke right here. Right? This is why you don't do it. Now, there's not a question on your homework where you have to go in and develop the complement. Well, remember, the complement is just the opposite. So if the probability of A was 0.25, right, then that's going to be the opposite of it. And it goes through exactly how they come up with those. But this is the stats in here is a little too difficult for the scope of what I'm teaching you guys. I really just wanted to get to these values to show you. There's evidence. And this is just males. I think females goes up a little bit more. All right. Okay. So on your homework, you won't have one that's quite that in-depth. But it's nice to see. It's nice to see the applications of all this stuff, right? Where does it actually apply to real life? Okay. So here we go. The Federal Trade Commission, the FTC investigation of consumer products complaints has generated much interest on the part of manufacturers in the quality of their products. We kind of have seen this, right? Definitely the quality of manufacturing in pretty much all products has went down. I mean, you can contribute that to a lot of things. I mean, most of the consumer products we use now are made where? In China, right? So they just don't have as much detail. You know, they don't spend as much money. The metals they use aren't as strong. I mean, all that stuff goes into why these things break down, all right? A manufacturer of an electromechanical kitchen utensil, which here's a blender, right, which fits that description, have analysis of large number of consumer complaints and found they fell into one of 6 categories, right? So did they fail? The guarantee period is the same as kind of the warranty, all right? So does it fail during the warranty period? If so, why? What failed? Right? Which this appearance must be like the paint chipped or maybe one of the labels fell off, where it still works, it just doesn't look as good, right, as the appearance. These two, it doesn't work, right? Electrical or mechanical. So here the electrical system goes out. Here, maybe something breaks on it, like the thing that attaches the blender piece, right? Breaks, so that's mechanical, right? So notice if the stickers are going to fall off of it, they usually happen very early as opposed to late. Can we see these numbers right here? That's what this is kind of showing. Okay? So let's go read a question. So here's our numbers. So what this is saying is 32% of all the complaints during the warranty period deal with their appearance of the item. Okay? If a consumer complaint is received, what is the probability that the cause of the complaint was the appearance of the product, given that the complaint originated during the guarantee period? Right? So what's the chances of appearance being the problem, given we know the complaint happened during the guarantee period? All right? So let's go through and read what happens here. This is kind of what we have to do on our homework. And a lot of the percentages all the percentages just go directly to probabilities, right? You just move the decimal over. Okay. Let A represent the event that the cause of a particular complaint is the appearance of the product. Right? Let B represent the event that the complaint occurred during the guarantee period. All right? So A is the causes in the appearance. So probability of A would be 0.35. Does everybody see that? So let's write that up. So A is the event that there's a complaint, which I'll just put comp, during guarantee So what's the probability of A? What's the probability that there's a complaint during the guarantee period? No, complaint in the appearance. Whoops, I wrote that wrong. Let A represent the event that the cause of a particular complaint is the appearance. Complaint due to appearance. I switched those two. So what percentage of all these complaints come from the appearance of the product? 0.35, because I don't, event A doesn't say anything about during the guarantee period or not. So probability of A is 0.35. We're going to let event B be a complaint. This one's during the guarantee period, right? Yeah. Complaint during, which warranty is another way to think about it. So how many complaints do they get during the guarantee period? What's that probability? Right. All these added together, the electrical, the mechanical, and the appearance, which is 0.63. Now, we may or may not use these in our formula. I just want to help write this stuff down, right, and start thinking about it. Okay. So here's probability of B is 0.63. The percentage of complaints that were caused by appearance and during the guarantee period. So what's the intersection of these two? Right. What's the probability that both happen?
0.32.
Right. It's going to be this value. Right. Just that one. The 0.32. Okay. Everybody see where I'm getting these from? Notice they come directly from the table, right? You just have to be able to read the table here. Using these probability values, can we calculate the conditional probability that the cause of a complaint is appearance? So the probability of A, given the complaint occurred during the guarantee time, given B. So what's the chances A happens given B? Everybody see what's going on here? Notice I'm going to use this value and this value, right? Those are the two things from my formula that I just erased. So according to the formula, the probability of A given B is always the intersection of these two events divided by the chances that the given event happens. We know both of these values, right? They were given us over here. So the probability of A given B is equal to the intersection, which is written here as well, which we found out was 0.32, given B, right? Given that the complaint occurred during the guarantee period. 0.63. And punch that in your calculator. And it should be 0.51. Well, let's really talk about why that happens. 0.32 divided by 0.63. Round it to two decimal places and we get 0.5. So let's interpret that 0.51. In English, let's interpret it. What does that mean? Of course, that's a wet erase, so I got to have a rag for it. What is that 0.51? What is that as a percentage?
50%.
50% of what?
Of the total complaints.
During the guarantee period. So notice how This ratio, 32 out of 63, put that in your calculator. What's 32 divided by 63? It's going to be the same number, right? That's exactly how they come up with that. So of all the complaints during the guarantee period, roughly half of them were because of the appearance. And it also comes from right here. So in English, just looking at this table, you know, you could probably come up with that without using this fancy conditional probability formula. Right? But this always governs it. This will always work. Sometimes looking at the table, there's some manipulation you have to do. But if you look at it, 32 out of 63 is roughly 51%. Which is why this is 0.32 and that's 0.63. It's no coincidence. So I could ask you here, what's the probability? So I'm going to write this up in English and see if you can come up with it. What's the probability of a failure from mechanical given after the guarantee period? So what's the chances that it fails because of mechanical given it's after the guarantee period? So I'm going to go probability of failure, and I'm going to call it FM. I'm going to use two values to represent that event. Rather than go and define it as A and B, I'm going to say FM, failure mechanical given after the guarantee. AG is what I'm going to call it. Which I like using that better because that actually represents something. Which you're welcome to do as long as it's defined correctly. So this means failure from mechanical given after the guarantee. So this is going to be equal to the probability of the intersection given the probability that it fails after the guarantee. Is everybody following along what's going on here? So what's this probability? 0.22. All the values that fail from mechanical after the guarantee. So that's 0.22. And what percentage of them fail after the guarantee? 37% or 0.37. 0.22 divided by 0.37. 0.59. So roughly 59%. So you have a 59% chance that after the guarantee period, which is usually like 12 months for this type of stuff, it's going to fail because of mechanical reasons. Notice the appearance stuff is what happens early on, and the mechanical stuff is what happens later on. Right? We kind of see what's going on here. So the appearance is basically the glue or something that, or the paint chips or something very small. So that's that. There is our conditional probability. Pretty straightforward, really. As long as you're given these values, it's really simple, right? You just plug it in. Plug and chug. Okay? Okay. Now let's move on to the next section. So this multiplicative rule of probability is really nothing crazy, right? It's nothing to really get all in a fuss about, because all it is multiplying both sides by P of A. It's basically solving for the intersection. So the way we get rid of this denominator is to multiply both sides by the denominator, right? By the probability of A. Which is something you might have to do, because you might be given the conditional probability and the probability of A, and then you got to solve for the numerator. Right? So let's look at that on the next page. So it's really the same formula, just manipulated a little bit. See? Multiplicative rule of probability, the probability of A intersect B is equal to the probability of A times the probability of B given A. So all they're doing right there is taking the general formula and multiplying both sides by P of B, by the probability of B happening. Everybody see what's going on there? What's P of B divided by P of B? What's something divided by itself? 1, right? It just goes away. So that implies, right, that reduces, so we get the probability of A intersect B is equal to that multiplication. P of B times P A. The only time you'd use this formula is if you're given these two values and not given the intersection. All right? And remember that multiplication is commutative. I can change the order of those and it's the same thing. Right? 2 times 3 is the same as 3 times 2. Question?
No,
Just writing it down. Okay. See, and that's why it says or equivalently. Notice how here they have probability of A because that's the second thing listed here. Here they have probability of B because that's the second thing listed there. All right? That's just from the formula. Because of this, right? Because of the conditional. The original formula. Nothing too crazy there. Here's an interesting example. Electroshock therapy. Anybody ever done this before? Now we've shown that it works for our joints, like it works for our bones. It doesn't really work for our brain, all right? It actually does a little more harm than good. That's why they don't do it anymore. In a classic psychology study conducted in the early 1960s, so that's our first clue. This one we're just kind of learning about this stuff. Stanley Milgram performed a series of experiments in which a teacher is asked to shock a learner who is attempting to memorize word pairs whenever the learner gives the wrong answer. This is like what you do for a dog when they bark, right? Isn't that kind of what it sounds like here? The shock levels increase with each successive wrong answer. Unknown to the teacher, the shocks are not real. So the teacher thinks they are. 2 events of interest are, so A is the teacher applies a severe shock. B, the learner protests verbally prior to receiving the shock. Right? So notice here it gives us P of B and P of A given B. It gives us the 2 values that we need. So all I'm going to do to get the intersection, right? What's the probability that A and B occur? The teacher applies a shock and the learner protests verbally prior to receiving the shock. That's just going to be the multiplication of these 2 values. That's all there is to it. All right. This would be difficult if I gave you a bunch of empirical data and I made you come up with these values. Right? Then it would get a little more difficult. But if they're given to you, you just plug and chug into the formula. You just have to remember what goes where. Thus, about 35% of the time, the learner will give a verbal protest and the teacher will apply a severe shock. All right? Notice this doesn't say anything about A. It doesn't say the probability that the teacher applies a severe shock. We don't really need it for this problem. But that's not what it's asking us. Okay? Okay. Now we're going to talk about one more thing. All right, and we're not really going to go over this example. We're more or less just going to look at the... Okay. This is an example about workers. All right. So let me kind of explain this tree diagram. Okay. What this tree diagram is talking about is workers giving illegal deductions to welfare recipients. No means no illegal deductions. I means illegal deductions. All right? So each worker basically is the same in the sense that 70% don't get illegal deductions, 30% do get illegal deductions. All right? So what we want to know is, does the fact that the first worker doesn't give illegal deductions, does that influence the fact that the next worker gives illegal deductions? Does one have anything to do with the other? All right? Another way to think about it is rolling a die. If I roll a die and get a 3, the next time I roll a die, it doesn't matter what I rolled the first time. Right? It has absolutely no impact on what happened the first time. And that's what's happening here. It has absolutely no impact. All right? Because look at the intersections of no intersect I and I intersect N. So the first worker doesn't give illegal deductions. The second worker does. Here the first worker does give illegal deductions. The second worker doesn't. You notice those two probabilities are exactly the same. Now you don't really need to worry about the background of this. What I want to show you here is that the first worker's thing that they did, right? The fact that the first worker gave deductions or not has nothing to do with the fact that the second worker gave deductions or not. That's what independent events are talking about here. Does the first thing influence the second? Here's how we test for independence. Independence is different than mutually exclusive. All right? Mutually exclusive means they have nothing in common. Right? Events A and B are independent if the occurrence of B does not alter the probability that A has occurred. Right? That is, events A and B are independent if. And here's just the formula. This is all I want you to write down. Notice here, it's got the first piece, right? So this is our probability for our conditional probability statement. All right, probability of B. So this is for conditional. And then our independence test. Independent if the probability of the condition is just equal to the probability that the first one occurred. So the probability of the given condition is equal to the probability that just the first event happened. So here's a way to think about it. If I was asking, what's the probability it's going to rain outside if I see birds flying? And maybe that's not good because birds do have a little bit of an effect on the weather. You know, they kind of know what's going to happen. So, what's the probability it's going to rain outside if I wear a yellow shirt? Those don't have, it's just going to be the probability that it rains outside. The fact that I'm wearing a yellow shirt has nothing to do with the fact that it's going to rain. That's kind of what independent events are. Okay? So notice here, if they're independent, then this quotient is just going to be equal to the probability of A. If they're independent. Everybody see that? Because this piece is the same. A given B, A given B. If this quotient, the intersection of A and B divided by the probability of B, is equal to just the fact that the first thing happens, then they are independent. Independent means the occurrence of one has nothing to do with the other one occurring. Okay? like dice rolls. Dice rolls are independent. Rolling a 3, given I rolled a 4 the previous time, is just the probability that I roll a 3. It's just 1 out of 6. The fact that I rolled a 4 the previous time has nothing to do with what's going to happen the next time. Okay? So that's what independent means. Pen. I better spell this right, huh? So this is our check for independence, right here. If that's not true, if the conditional probability is not equal to the probability of the first thing happening, then they are dependent. Then it does have something to do with it. All right? And here's a good example on the next page. Okay, so let's talk about independence. Consider the experiment of tossing a fair die, so a 6-sided fair die. Event A is observing an even number. Event B is observe a number less than or equal to 4. Let's think about this. Let's just think about the probability of each separately. Right? So the probability that we will observe an even number, just in general, is the probability of getting a 2 plus a 4 plus a 6. There's 1/2, right? Probability of getting an even number. We've seen that a bunch of times. Probability of B, observe a number less than or equal to 4. So that's 4 out of 6, right? There's 4 numbers less than or equal to 4 on a die out of 6. So that's 2/3. Okay? So that's how we come up. Does everybody understand how I came up with probability of A and probability of B? There. So the probability of the intersection that it's even and less than or equal to 4 is 2 out of 6, right? Because we want it to be able to fit both conditions. So the number has to be even, so it's either going to be a 2, a 4, or a 6. And it has to be less than or equal to 4. So I'm kicking the probability of rolling a 6 out. So all I care about is 2 out of 4. 2 out of 6, excuse me. 2 and 4. Which is 2 out of 6, which is 1/3. All right, so here's my probability of A, probability of B, and probability of the intersection. So that's the probability that event A occurs and event B occurs. Is 1 out of 3. So I have a 33% chance that when I roll a die, I will satisfy both events. Does everybody agree with that? What's going on here? Okay. Now, assuming that B has occurred, so we observe a number less than or equal to 4. How many numbers are there on a die that's less than or equal to 4? 4, right? Right here. 1, 2, 3, 4. There's 4 numbers. How many of those 4 numbers are even? 2. So the chances that it's even, given we know it's less than or equal to 4, is 1/2, which is exactly the probability that it's just even in general. So right down here, they punch it into the to the formula. Probability of A given B is 1/3. Probability of B is 2/3. Does everybody know how to divide fractions right there? Let's do that for practice. So what I'm going to do, let me pull back. All right. So the probability of A given B is equal to the probability of the intersection divided by the probability of the conditional, right, of the second thing. So I know the probability of A given B, or A and B. So the probability that the number is even and less than or equal to 4 is 2 out of 6, which is 1/3. The probability that the number on the die is less than or equal to 4 is 4 out of 6, or 2/3. Let me do that a little bit different. Let me write that. So how do I divide a fraction by a fraction? Does anybody know the method? Multiply by the reciprocal, or we call it keep, change, flip. Have you guys ever heard that statement, keep, change, flip? So what we do is we keep the first one, we change the division to multiplication, and then we flip the bottom fraction over. So 1/3 divided by 2/3 is the same thing as 1/3 times 3/2. And notice 3 over 3 goes away, so our answer is 1/2, which is equal to the probability of A. Right? Does everybody see that? Probability of A is 1/2. Isn't that how we test for independence? If the probability of A given B is equal to the probability of A, then they are independent, right? That's what my independence rule is. If the probability of A given B is equal to the probability of A, then they are independent. I can show here that the probability of A given B is equal to the probability of A. So A and B are independent. Another way to think about when you divide fractions, the two things in the middle get grouped together, the two things on the outside get grouped together. So this 1 and this 3 go together, and the 3 and the 2 go together. Everybody see that? So 1 over 3 and the 3 over 2. Same thing. So since this given conditional probability was equal to the probability of the first thing happening, these two events, A and B, are independent. If this would have been 1/3, then they wouldn't have been independent. They would be what's called dependent. Okay? So I'm going to ask you on your homework, I'll ask you a question like this, right? First, find the conditional probability. Then I'll ask you if the conditional probability is independent. Now, you won't really have to do this part, okay? The probabilities will already be given to you. You'll just have to plug them in, okay? Plug and chug. All right? Let's see what else we got here. Okay. All right, last thing I want to talk about is the probability of the intersection of two independent events. Right? So let's go back and just look at the right-hand side of this equal sign. So if two events are said to be independent, right? I've already said that this has to happen. Right? Does everybody know? We've talked about that. Right? The probability of A given B has to equal the probability of A. Now, if I know that happens, and I know the probability of A given B is always equal to this, then that means this and this have to be equal. Does that make sense? If I know they're independent? If I know A and B are independent, then when I take the probability of A intersect B divided by the probability of B, it's always equal to the probability of A. So what I want to do is, so I know A and B are independent, all right? That's given. I want to solve that equation for the intersection. So I'm going to solve it for this. So what do I do to solve this equation for the probability of A intersect B? What do I multiply both sides by? To solve for the intersection. So I want to do some math and get to this point where I have P of A intersect B is equal to something.
Probability of A times probability of B.
That's the final answer, and the way that I do it is by multiplying both sides by the probability of B. So that on the left-hand side they go away. So on the right-hand side I get the probability of A times the probability of B. So if I know A and B are independent, and notice how all this stuff we've done today kind of follows directly from that formula. Right? So if I know A and B are independent, then their intersection is just multiplying the two together. What page is it? 43. Right here. Now, look at this. Mutually exclusive events are dependent. So the word independent and mutually exclusive, even though they kind of mean the same thing in English, they do not mean the same thing in statistics. Mutually exclusive means their intersection is zero, right? They have nothing in common. For this intersection to be zero, either the probability of A or the probability of B would have to be zero. So if two events are independent, they are not mutually exclusive. All mutually exclusive events are dependent. Okay? So independence and mutually exclusive are different. And that's one of the hard things from this entire chapter, is to keep those two things separate. Mutually exclusive means their intersection is zero. There's nothing in common. Here is a picture of mutually exclusive. Mutually exclusive events are dependent because they don't follow this rule. Right? Okay, now let's get to this point. So the probability, if A and B are independent, so that has to be given. They are independent if their conditional probability is equal to the first probability. Right, the first thing given. Right, the probability of A given B is equal to the probability of A. Means they're independent. Then the probability of the intersection of A and B equals the product of the probabilities of A and B. All right? So the probability of the intersection is just the multiplication of the two probabilities. So really what independent means is the fact that the first one happens has nothing to do with the fact that the second one happened. So let's do this in a coin toss example. All right? So I'm going to erase this. I'm going to leave that formula up. So I'm going to define two events. I'm going to let A equal the event flipping a head. So I'm going to flip a fair coin, and I'm going to let A be the fact that it's a head. I'm going to let B be the event is the second flip is a head. Okay? So I want to know what's the probability of both of these things happening. Now notice that the conditional probability, the probability of A given B, they don't have anything to do with each other. They are independent events. But their intersection is not zero. Right? So I know these are independent events. My first flip, whatever it is, has nothing to do with my second flip or vice versa. Does everybody agree with that? If I flip a coin once and get ahead, my next flip, it does not matter what happened the first time. That means they're independent. That's not mutually exclusive. Right? That's different. So here, since these events are independent, I know the probability of the intersection is equal to P of A times P of B. Because these can both happen. So their intersection is definitely not zero. Does everybody see that? Because I could get A and B. It's possible for me to flip two heads in a row. That would be the intersection. So our intersection is definitely not zero, right? Which would mean they were mutually exclusive. And this is how they come up with probabilities for all kinds of stuff, all right? So what is the probability of flipping a head? 1 over 2, 1/2, right? So it's equal to 1/2. What's the probability of my second flip being a head? 1/2. 1/2 times 1/2. So my chances to flip two heads in a row is 1/4 or 25%. Which is exactly what happened in the examples where we've done two coin flips. Right? Like that tree diagram. You don't get it.
Can we put those into decimals
Yeah, oh yeah, absolutely.
instead of
Yeah,
fractions?
absolutely. So let's just look at this chart on 115. If I flip a coin twice, there's 4 things that can happen. And all of these 4 outcomes are all equally likely. Right? You guys agree with that? So how many of these 4 outcomes are flipping ahead both times? 1 out of 4. Same thing. So what would be my probability of getting ahead 3 times in a row? So if I did another one, I did B is equal to the third flip is ahead. What's the probability of the third flip being ahead? 1/2. What's 1/4 times 1/2? 1/8. So you have 1 out of 8 chance of getting 3 heads in a row. If you do it again, you have 1 out of 16. Then you have 1 out of 32. Then you have 1 out of 64. So notice your probability really goes down a lot each time you flip the coin. That's kind of how the stock market works. There's a piece within the stock market, it's called stochastic calculus, where there's a lot of things that go into it from the economy and price of goods, but there's one piece that is essentially a coin flip. It has a 50% chance of increasing and a 50% chance of decreasing. That's why whenever a stock's been gaining for a long time, you know, the probability states that it's bound to fall because it's been hitting, you know, you've been hitting so many heads in a row that you would expect the next one to be a tail if you've done 3 or 4 in a row. That's kind of what happens with the stock market. That's why they say you sell when it's high and you buy when it's low. Because if it's falling, it has a higher probability of coming up. If it's gaining, it has a higher probability of falling off. This is actually the same way you would come up with a royal flush, the probability of getting a royal flush. It would actually be 1 out of 52, because there's only 1 out of 52 cards. Say if you got a royal flush in spades, you need an ace of spades, a king of spades, a queen of spades, a jack of spades, and a 10 of spades, right? You guys kind of follow me on that for the people that have played some cards before? So the probability of getting a royal flush, which are independent events, right? Just because my first card was an ace of spades, that has nothing to do with what my next card's going to be. Now, I know it's not going to be the ace of spades, but it could be any of the other 51 cards. But it has no influence. So the probability for a royal flush would be 1 out of 52 times 1 out of 51, because out of the 51 cards that are left in the deck, there's only 1 that I need. Right? Times 1 out of 50 times 1 out of 49 times 1 out of 48. And that's actually not quite exactly right. There's something we need to do with the numerators. So out of the 52 cards in the deck, I need one of the 5. Right? So that would be 5 out of 52. So say I got the ace of spades, so there's still 4 cards out of the 51 I could get dealt that'll help me get a royal flush, right? So the next one, there's 3 left, right? Say if this is the ace and the king, there's still the queen, jack, or 10. So it would be 3, and that would be 2. That's your probability of getting a royal flush right there. Yeah?
Wouldn't you have to take into account the other players?
Yeah, no, I'm just saying dealing it to yourself. Yeah, that's a very good question. Right. Yeah, if the other people are getting cards, then that makes this much more difficult. I'm just saying dealing it to yourself. So you shuffle it 7 times, you deal yourself 5 cards. What is this number? It's going to be something very, very small, right? 5 divided by 52 times 4 divided by 51. So I'm doing each one separately, so the order of operations isn't a problem. So I'm doing each of these kind of in parentheses. Times 3 divided by 50 times 2 divided by 49 times 1 divided by 48. You get 0.123456385. Or, which is equal to 0.1234385%. That's your chances of getting a royal flush. You're not very good. Maybe if you play poker online, you might see one. But in your whole life, unless you're like a professional player that plays, 500 hands a day, you'll probably never see a royal flush dealt in competition. Ever. Because look at the chances. And it's not like each hand you play, this keeps getting added to it, right? This is the chances every single hand. Because they're all independent, right? What you got the first hand doesn't have anything to do with what you get the second hand. So your chances of getting one are very, very small. That's why this pays out the most. And we can come up here and change this around and say, what's the chances of getting 4 of a kind? Well, the first one, it doesn't even matter what card you get dealt. Right? The other 3 you'd have to change depending on what this first card is. Then the last card doesn't even matter. Right? So for 4 of a kind, it would be something like, the first card doesn't matter what you get. Right? Because 4 of a kind could be any of the cards. So it would actually be 52 out of 52. Just give me a card. Then depending on what this first card is, say if it's an ace, how many aces are left when they deal the second card, when you deal the second card to yourself? 3. So this will be 3. This will be 2. And this will be 1. What about the 5th card? Does it even matter what it is? Nope. It has no bearing. So that'll be 48. That's the probability for dealing yourself 4 of a kind right there. So this number's 1, that number's 1, so really all we care about is this. Look how much bigger probability this is. So 3 divided by 51 times 2 divided by 50 times 1 divided by 49. This one's 0.000048, which is equal to 0.0048%. And the other one had, what, 4 zeros in it on the percentage? So you're 100 times more likely to get 4 of a kind than you are to get a royal flush. 100 times more likely. So this is 4 of a kind right here. So then a pair, you can see why a pair is so likely, because the first card doesn't matter. Then the second card would definitely be 3 out of 51, right, to pair up the first one you got. And these other 3 cards don't even matter, right? They would be 1. So your chances of getting a pair is 3 divided by 51. Or about 6%. Dealing it to yourself. So you have a 6% chance, if you deal yourself 5 cards from a randomly shuffled deck that you'll have a pair. Which, the reason I wanted to get to this section is because of this stuff. Now, I find this stuff really pretty interesting. Probability is really a neat thing. It's very applicable. And that's something you'll have to do for your majors. You know, if you're a sociology major or even an SLP major, and you say that 20% of all kids suffer from maybe from dyslexia. What's the chances that one kid will suffer from dyslexia given they've been held back in class? Things like that are the stuff you have to talk about. That's why you have to take this class for those majors. So independent things are very, very important. This is why the Challenger space shuttle, which most of us in here weren't alive when that happened in 1980, this is why the Challenger exploded. And the reason is because it had these bolts that kind of kept together part of the fuselage. I think it was the rocket booster tanks, all right? And those bolts had like a 98% chance of not failing, which is still pretty low when you talk about airline stuff. But there were 6 different bolts of that kind on one of those rocket boosters. So each one had a 98% chance of success. So if even one of them goes out, though, the thing blows up, right? So what happened was, the way that they came up with it was they did 0.98, which is the chance of success of one bolt, but the fact that the first bolt succeeds has nothing to do with the fact that the second bolt succeeds. So they were independent. So what they did is they multiply it together for all 6 bolts. So all of them have a 0.98% or 0.98 or 98% chance of success. So this is equal to 0.98 to the 6th power, right? You guys agree with that? Times itself 6 times? Put that in your calculator. That's the number you come up with is the chances that all of them succeed. What's 0.98? Does everybody know how to use a different exponent? It's a little up-pointing arrow called the caret. Let's go and look at that. So we want to know the intersection of all this, right? What's the chances that the first bolt succeeds, and the second bolt succeeds, and the third bolt, and the fourth bolt, and the fifth bolt, and the 6th bolt? Because if even one of them fail, the thing goes kaboom. So what is 0.98 to the 6th power? And this is the caret key to give you an exponent, is this little up-pointing arrow. 0.98 to the 6th. That means you had an 88% chance that all of them would succeed. Or a 12% chance that at least one will fail. And that's what happened. One of them failed. That's way too high of a probability that, that should have been caught by the engineers, but it never was. Because they weren't really statisticians. They weren't thinking about that. The fact that all those bolts were independent of each other. 88% is definitely not something you want to, 88.5% or even 89% is not something you want to risk your life on. 98 maybe, definitely not 89. Right? So that means if they launched that rocket 100 times, 12 times it would explode. That's way too many. Right? That's what happened with the Challenger explosion. And I watched a cool video about this exact thing when I was in Stat 213. So that's why I'd like to bring it back. And I've looked for it everywhere, but I can't find it. But pretty interesting, though, that stats could really go in and talk about. That's why airline mechanics have to be so stringent. That's why all their tolerances are so stringent, because a lot of those things don't have anything to do with each other. Right? They're all independent. The fact that the wing stays hooked on has nothing to do with the fact that the engine on the right side doesn't fail. So they have to multiply all those probabilities of failure together to make sure that nothing bad's going to happen. Which is really interesting if you think about it. Right? Who would have thought stats would have something to do with that? Okay. So there's 3, 4, and 3, 5, or 3, 5, and 3, 6. I have some time, so let's jump into 3.7. It's a really simple, straightforward section. All right. It's actually only 2 pages long. Oh. I wonder it doesn't. Okay. How a sample is selected from a population is of vital importance. Let's make sure this is on the screen. So how a sample is selected is vital. So in my card examples of where we were coming up with Royal Flush and Four of a Kind, the fact that that deck was randomly shuffled is very important, right? If that deck wasn't shuffled at random to begin with, then we have a problem. Like when you get a brand new deck that's always in order, right? The suits are in order. You definitely wouldn't want to pass out a brand new deck. Like that's not random at all. So that's what this is saying. How a sample is selected from a population is of vital importance in statistical inference, because the probability of an observed example will be used to infer the characteristic of the sampled population. To illustrate, suppose you deal yourself 4 cards from a deck of 52, and all 4 cards are aces. We've already seen the chances of that happening was 0.004%, or less than 0.5%. Do you conclude that your deck is an ordinary bridge deck containing only 4 aces, or do you conclude the deck is stacked with more than 4 aces? Depends on how the cards were drawn. If the 4 aces are always placed at the top of a standard bridge deck, drawing 4 aces is not unusual. Now, I've never played bridge, so I don't know exactly how that's done. It is certain. If, however, the cards are thoroughly mixed, drawing 4 aces in a sample of 4 cards is highly improbable. We just saw that, right? I came up with that number. It was 0.004%, which is very, very small, right? The point, of course, is that in order to use the observed sample of 4 cards to draw inferences, you need to know how the sample was selected. One of the simplest and most frequently employed sampling procedures is applied in the previous examples and exercises. It produces what is known as a random sample. So this section talks about how to produce a random sample. Basically, the best way to produce a random sample is to remove human intervention. People cannot be the ones making the sample. Right? That's why we shuffle a deck so much, right? So that humans don't have anything to do with it. No, we might be the one passing out the cards, but we don't have any input in what card gets passed out. Okay? We learned in section 1.5 that a random sample is likely to be representative. If a sample is selected at random, we're pretty sure it's going to be representative. The laws of chance do a very good job in making the sample representative. That's what random is, right? It's the laws of chance. So let's define random sample with a very systematic approach. If n elements are selected from a population, so if I select 4 cards from a deck of 52 in such a way that every set of n elements in the population has an equal probability of being selected, that means I've shuffled the deck thoroughly. So any of the 4 cards are equal to being selected. The probability of being selected is equal to any other 4 cards being selected. Then the n elements are said to be a random sample. What that means is every member in the population has an equal chance of being a member of the sample. A good example of that is the bingo parlor. Right? In a bingo hall, you would think that every single ball in the bingo chamber has an equal chance of being selected as any other ball. That is a random sample. So if I was going to randomly select one student from all the undergrads at Eastern, I need to make sure that I'm not just selecting from males or females, or just selecting from seniors, or just selecting from freshmen. Every single undergrad should have an opportunity to be part of the sample. That would make it random. A good example of this is drawing straws. Drawing straws is a random sample because each member of the population, each straw in the person's hand, has an equal chance of being selected. That is a random sample. All right? Now, the person holding the straws can't be the one making the pick, right? Because they're biased. They know which one's short compared to the other ones. All right? So if I put the population is not too large and the elements can be numbered on slips of paper, poker chips, etc., you can physically mix the slips of paper or chips and remove n elements from the total. Another way to think about this is when you're doing, has anybody ever done the Super Bowl squares? The big 100 or 10 by 10 chart? Now you need to make sure that when the numbers at the top of the columns are selected at random, right? They can't just be 1, 2, 3, 4, 5, 6, 7, 8, 9. Really, the way I've always done it is I'll write 0 through 9 on a piece of paper, crumble it up, put it in a hat, and draw them at random. That's the fairest way to do it. Right? So that's what randomness means. So the first time I draw a number out of that hat, every single one of those 9 numbers has an equal chance of being selected. That's a random sample. Okay? The reason we don't let humans do this is, I can't tell you, go out to Portales and randomly interview 10 people. Humans can't do that. Because what if you walk up to somebody and maybe they are wearing a scary picture on their shirt and you don't want to go talk to them? You have removed that person from your study. Therefore, it is no longer random. So humans are not good at selecting at random. We actually can't do it. It's impossible. Which is really pretty crazy. That humans can never select at random. So there's this dichotomy whenever we're doing surveying, the population, that you want to make sure that your subjects are selected at random, but you want people to go ask the questions because they're less likely to fill out a piece of paper. Or to fill out your, when you're going on the internet and you get a little box that pops up that says, would you like to fill a survey? What do most of us do? No thanks, right? Or hit the X and clear the thing off. So there's this dichotomy that they have to do. People can't pick who's going to get questioned, but you want people to question the people that get picked. All right? So that's why it's difficult. Since it's often difficult to achieve a thorough mix, such a procedure only provides an approximation to random sampling. Most researchers rely on random number generators, which is just a computer that picks numbers at random. The computer is not biased. All right? Random number generators are available in tabular form, are built into most statistical software, and are available on the internet. Actually, your homework assignment in this section, it shows you how to create a random number in StatCrunch, which is really pretty simple. There's a couple buttons you click. All right? Really, if you go online, you can find random number generators. There you go, random.org. So right here, true random number generator. So this is going to send me a list of 1 to 100, and it's going to put the numbers in completely random order. This would be a good way to select somebody, say of 10 employees at a certain place, they need one person to stay on the weekend and work overtime. The best way to pick somebody at random is to give everybody a number. So I can number everybody in this class, say 1 through 9, right? So let's do that, 1 through 9. And randomly selecting one, the last thing I would want to do is say, well, I'm going to have this person do it. That's not a random selection. The first number that shows up in this list, boom, 3 would be the random result. That's just like drawing a number out of a hat, right? So that is a random number generator. And what this means is if I keep pressing this button, and I write down which number that gets generated, in the long run, every single number from 1 through 9 should have the same amount of times generated. should basically be 1 out of 9, right? Or about 12%. Every number should show up about 12% of the time. Now that doesn't mean that if I press it again, I might get a 3 again, right? Random or probability means in the long run. So if I press this generate button 10,000 times, I would expect each of the numbers 1 through 9 to show up about the same amount of times, all right? That's what it means. So look, 3 came up again. There it was. Oh, I think it's doing the same thing. No, look, 3 did 3 times in a row, but then it's 8, then it's 5, then it's 6, 4, 9. So I'd want to write these down and keep doing it over and over again. The proportion of each number would eventually be the same, right? In the long run. Okay? So that's one way you can generate a random number. All right. So your other questions for this section is to just use your combination formulas of n choose n. Suppose you wish to randomly sample 5 households from a population of 100,000. So how many different sets of 5 can you make from 100,000? Well, a bunch, right? And really, I would punch it into our formula and come up with this number. 8.33 times 10 to the 22. So that means there's 22 places we need to move that decimal over. I mean, I don't even know what the name of that number would be. It's a billion trillion. So it's a billion times a trillion. 83.3 billion trillion different samples of 5 households. Use a random number generator to select a random sample. So you actually learn how to do this in StatCrunch, and it creates, and actually in your textbook there's this as well. What page did it say it appeared on? Do you have the page number? It's in the appendix. But what it's got is a random number generator here. So you would just pick 5 values out of it. And this is something that will be given to you in your homework. So these numbers were just completely generated at random. If I went through and counted this, I should have the same proportion of 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s. Now, I would want a bigger sample, but those are just random numbers that have been generated. So it's not too crazy here. This section's pretty straightforward. It just really talks about the definition of a random sample. All right? So let's look at one more. Randomization in a designed experiment, a clinical trial. Anybody know what a clinical trial is? That's basically how everything that the FDA approves for our consumption has to go through some type of clinical trial. All right? So if any of you take Zyrtec for allergies, right, or any of these other thousands of pharmaceutical drugs, they all have to be proven through a clinical trial. A clinical trial is a special form of designed experiment. A designed experiment involving human subjects is a clinical trial. So you guys have probably heard this a lot, that Bayer saves your life, right? Bayer is a type of aspirin. Does aspirin really help prevent heart attacks? And we've always heard this our whole life. But is it true? Well, the way that they prove it is by a clinical trial. Now, what's very important here is that your people taking this drug were picked at random, and they get divided into these 2 groups at random. Right? You can't pick the people that are over 50 and put them in the treatment group, and people that are under 50 and put them in the control group. Basically, the difference between a treatment and a control group is the people in the treatment group get the aspirin, and the people in the control group get a sugar pill that looks like aspirin. We call that a placebo. The reason we use a placebo is because our brain is really it's a miracle object in the entire universe. There's nothing really like the human brain. The fact that we can think we're getting a drug will actually give us positive results. You could give somebody a sugar pill and tell them this thing is going to make you run 100 miles an hour. And in 2, 3, 4 weeks, they will actually run faster than they did when they started because they think they're supposed to. Golf is an excellent example of this. When you're standing over a shot or you're in a certain situation and you don't think it's going to go well, it doesn't go well. If you think it is going to go well, it usually does go well. And that works in everything. Right? Just about anything you do in your everyday life. If you think it's going to go well, it usually does. If you think it's not going to go well, it usually doesn't. All right? One recent trial was for heart attacks. Volunteer physicians were randomly divided into two groups. So they're actually putting the doctors into the two groups. Into a treatment group and a control group. They need the control group because they need kind of a baseline to see if the people in the treatment group are doing better. Right? That's why they need the two groups. Just like when you're doing an experiment in a science class. Right? If you're using Miracle-Gro on one plant and just regular water on the other, you want to make sure that everything is the same between the two plants. They get the same amount of sunlight, they have the same amount of soil, same percentage of nitrogen. Everything's the same except for the fact that one's getting Miracle-Gro and one isn't. Right? Each physician in the control group took one aspirin tablet a day for a year, while the physicians in the control group took an aspirin-free placebo, basically a pill that looked exactly the same, but it was just salt, right, or water. You probably wouldn't want to use salt because that could have an impact on your heart. But it's some other thing that doesn't have any impact. An aspirin-free placebo made to look identical to an aspirin tablet. Since the physicians did not know to which group or which group the treatment or control they were assigned, because it's no use giving the ones in a control group a placebo if they know it's a placebo. You've invalidated it, all right? They call that a blind study. A blind study is when the subjects do not know whether they're in the control or the treatment group. Now, the people administering the test still know, all right? So they can't really have any contact with the physicians because they could unknowingly give the physician an idea of which group they were in, all right? Assume that 20 physicians volunteered for the study. Use a random number generator to randomly assign half the physicians to the treatment group and half to the control group. Really, you want these two groups to be statistically similar in every way. Have the same amount of males as females. Have the same amount of people over 50 as under 50. Right? Have the same. Maybe some of these physicians have suffered from heart problems in the past. You want to make sure these two groups have the same amount of people that have suffered from heart problems. Right? You want to make sure that one group doesn't have all three and the other group doesn't have any that have suffered from heart problems. And the best way to divide these two groups is by random selection, which is really pretty amazing when you think about it. Because you'd actually think, well, wouldn't it be better if a human went in and made sure that these two groups were statistically similar? It's actually no. Randomization actually does a better job. Right? That's why we allow students to pick their own classes. That's why we don't assign classes to students. Because we want a random selection. That way we can compare all the different statistics classes on campus. Because they were basically constructed at random. Right? Because we want to make sure that one class doesn't have all the students that have got an A in biology 113 and one class has all the students that have got a C in 113. Because then they wouldn't be statistically similar. Then we couldn't compare them. Right? Essentially, we want to select a random sample of 10 from the 20. The first 10 selected will be assigned to the treatment. The other 10 will be in the control. The Minitab random sample procedure was employed during producing the printout shown in Figure 322. Right? So what they did is they took their 20 physicians, they named them 1 through 20, and then in the treatment group, they randomly picked 10 of those 20 numbers. So the other 10 would be in the control group. That's a random sample. Right? Which you've noticed something there. You would expect the average of both of those groups, since we're naming them 1 through 20, you would expect the average to be about the same in both of the groups. If I averaged the numbers in the treatment group and averaged the numbers in the control group, the averages would be about the same. Which is really a pretty amazing thing when we're just selecting at random. Now, it doesn't give us any results of the study, which isn't very cool. But obviously it's shown that it works. I mean, we hear that all the time. Right? You've actually heard that if somebody's having a heart attack at the time, giving them aspirin can actually save their life during the heart attack. Because aspirin thins the blood. And it's a blood thinner. Okay. So this section's not very difficult. It's basically, I ask you some questions, like define a blind study, and it's multiple choice. All right. So this section's pretty straightforward. You have a few questions where you have to do something, choose something, 10 choose 2. I actually did that one in class yesterday when I didn't really need to. All right. Okay. So let's go glance at the homework. Because that's all I'm going to cover for today. That's enough. So that's it for chapter 3. Right? So 3536. So these two assignments, notice I have 3-2 for 622. I'm going to change that to tomorrow by midnight. Because I'd rather get through this stuff and then have a little more time to review than not have time to review. You know what I mean? So 3536, preview. Let's look at this one. So just answer what the formula is here. All right, look at the formula from the book. What thing should be in the denominator? Probability of A. So I know it can't be B or C. Is it the intersection or the union? It's the intersection, right? So it's A. It's always the intersection of the two values. And remember, A intersect B is the same thing as B intersect A. These two things can be switched. Right? Because it's what they have in common. So there's it. So you can check it. And there it is. So some other homework assignments. Where I ask you to find A given B, B given A, and are they dependent? I give you all the values. Right? Let's go ahead and do this one. It's a good practice. Can everybody see that? For two events, A and B, the probability of A is 0.5, the probability of B is 0.2, and the probability of the intersection is 0.1. So they're definitely not mutually exclusive, right? If they were mutually exclusive, this would be 0. They would have nothing in common. So the probability of A given B is equal to the probability of the intersection divided by the probability of what? Of the given thing happen, right? Because B has to happen. So this is equal to 0.1 divided by what? 0.2, which is 0.5, right? 1/2. Let's go back over here. So 0.5. There we go. So now let's do B given A. Probability of B given A. Notice that the numerator is not going to change, right? So B says the probability of B given A, the only thing that's going to change is the denominator. Is 0.1 over what? 0.5, which is 1/5, which is 0.2. How do I test for independence? What do I do to test for independence? What's the definition of independence? Probability of the first thing, right? So is this equal to the probability of B?
Yes.
Another way to test for independence is if the intersection is equal to the two events being multiplied together, right? So that's why I put a question mark here. So C, does the probability of A intersect B equal the probabilities multiplied together? Which is the way I like to think about independence. Which this is what happens in the real world, right? This is when we play cards. I mean, a bunch of different events. Is the intersection equal to those two things multiplied together? What is 0.5 times 0.2? 0.1. So the answer there is yes. And it asks us to verify using a formula. So which one is it? D, E, or F? So are they not equal? Is the probability of B given A equal to the probability of A, or is the probability of A given B equal to the probability of A? It's this one, right? It's always the first thing. Which is what happened here, right? The probability of B given A was equal to just the probability of B, right? Of the first thing happening. So since that did happen, the answer is yes. The events are independent. Okay? And once again, keeping independent and mutually exclusive separate is kind of hard, right? That's the hard part with this section. Ready? And then the other stuff from this section follows straight along. Here you have to come up with the percentages by just dividing good service and lunch 44 by the total 135. That's how you come up with the percentages. So it gives us the frequency. You want to change it to a relative frequency. So this problem is just like the one we did for the manufacturer stuff. All right? It's just like that. So get in there and try it. You can also open it in StatCrunch and play around with it in there. Hopefully it opens on this computer. And there it is, and you can get in there and mess with it. All right? Okay, so there's that section. You still have your view and example stuff. So if you get stuck anywhere, click it, and it'll go through and show you how to do it. Okay? Three 7, it's pretty straightforward as well. How to use a random number generator in StatCrunch. So there's a video on that. And there it is. It's only 3 minutes long. Really, really short. And then question 1. I think the first question says, what is a random sample? All right, so that comes directly from the book. A random sample is where every set of n elements has an equal opportunity to be selected. All right, that's the definition. Just like in the textbook. Then I asked to define what's a representative, what's a blind study, and then I ask you to do 3 different questions of randomness. And you're basically doing one over the other. Right? So pretty straightforward, this 3-7 is. Okay? Where we will start tomorrow, and I'll just go to the very first page, just so we can kind of start thinking about it. is we really haven't done any analyzation, right? Up to this point, we've just learned how to analyze. We haven't really been given anything and come to any conclusions yet. We start that in this section. And maybe you guys remember this from 106. So tomorrow in class, I'm expecting to have some questions over the stuff I assigned today. All right? I'm definitely expecting some questions. So we're starting this section, which is discrete random variables. What does it mean for something to be discrete? You guys remember from 106? Countable. That's it. You can count it. The number of people in this room is discrete. The distance from where I'm standing to the wall is continuous. Right? So we'll talk about those two different things and why they're different. Right? Rolling a die is discrete. Right? It's countable. Taking the temperature outside is continuous. Right? So in this section we'll cover 4, and then we'll take a test. Right? Probability distributions for discrete random variables. Expected values, which is really very cool. Right? Expected values are is how we determine if I played a roulette table and I put $5 in every time, what's my expected value? You basically expect to lose $1 every time you play. So you lose money in the long run. Every single game in a casino has a negative expected value. Except for, poker's not really a casino game. It doesn't have a negative expected value. That depends on how good you are. But the one at the smallest negative value is craps. So if you played craps over and over again, you would expect to lose less money than the other games. You still would expect to lose. Right? That's what we'll talk about with expected values. And then we'll get to binomial random variable, which is success or failure, which you guys did a project in 106. Remember that big ugly formula? The P and the Q? That's what we'll talk about there. And the way to think about that is, say somebody's a 70% free throw shooter. What's the chances they make 10 out of 10? We'll actually come up with a value for that. All right? So that's where we're headed tomorrow. So this test will have probability and discrete random variables. Discrete means countable, as opposed to continuous, which is an interval of numbers. All right? The normal curve is a continuous thing. All right? It's not discrete. Okay? So we're really moving right along in this class. Really, starting this, it usually takes about 4.5, 5 weeks to get to this point. So we're right about there, because this is the middle of the 3rd week, which is like about 5 weeks in a normal class, right? Because we're double time. So we're right on pace, doing good. All right? So come with me for questions tomorrow. All right? Because I definitely think there will be some, especially from 3.5 and 3.6. All right? Thank you, everyone. Have a wonderful day. We got one more day this week. Then you get the weekend off, all right? Where's my sign-in sheet? You got it? Okay. Thank you. That's right. Okay. Yeah, remember, Haley has hours today, but then she'll be gone, so go and see her. Thank you. You have any questions about your exam?
No, I don't think so. I'll go over it a little bit.
You kind of see why you missed what you missed. Okay, no problem. What do you guys think about this stuff?
I like it better than I thought it was going to.
That's kind of what happens with stats. It's really, even the next 2 chapters are pretty cool. It's when we start getting to hypothesis testing that it gets kind of boring. The H-naught, HA, two-tailed test, all that. But, the probability stuff is awesome, man. I'd like to just take a class on that,
because last semester when I took it, it's a lot different now because we didn't go over like more than half of the formulas that we're talking about here.
Really?
It's like, so I was kind of lost. It was almost like you were just kind of expected to know it. And so,
Yeah, there's really no expected knowledge in here other than some simple solving an equation, being able to divide both sides by something. That's about the only expected knowledge that you have in here.
so I like this one better. I feel like I'm able to grasp it.
That's good. You guys are good on your exam, so you got a good step, a nice foundation for the rest of the semester.
Yeah, I have to pass.
Right.
Well, you just come to class every day and pass.
Is if Clovis has a nice course? I heard that they do.
It's not bad. Yeah, it's pretty nice.
I was trying to.
It's green now. All the courses are green around here now, except for the basics underwater. Well, it's probably not now, but it was over the last month.
Oh, it was horrible. It was like completely washed out. There was like so much just freaking.
Because that's where everything was set up to drain to.
Right.
Because I had a friend of mine, well, his father-in-law's been the club champ out there like 4 years in a row. His name's Greg Terry. And he's like, I'm not even going back. I guess it's in bad shape. But I'm a member out here. There's a country club here in Dallas too, 9-hole. And it's in good shape because it's been raining so much. But, yeah, I like to play. I'm about a 10 handicap.
Just never had the opportunity to really play.
No?
I should have been nice and great.
Yeah, the Koreans are really
Like out there playing in the fucking snow. I was like, how do you see a damn golf ball in the snow?
The President's Cup this year is going to be in South Korea.
There's actually a really nice course on Osaka Air Base.
And the Korean women dominate the women's game.
You'll just randomly see because it's so.
The men don't hit it far enough to dominate the men's game. They're just not quite big enough. There's still some really good Korean players, but they don't dominate like the women, man. I think of the top 10 women in the world, I think 6 of them are Korean. And